This video is presented by AmazingPhysicsForAll.com. Have you really seen a rainbow? Most likely you have looked at rainbows, but have seen none. Have you ever noticed and admired the various parts of an awesome rainbow? To quote Professor Walter Lewin of MIT, so many of the little wonders of the everyday world which can be truly spectacular go unobserved most of the time because we haven't been trained how to see them. Look at this awesome rainbow. Can you tell the difference between primary and secondary? Why there is a dark band between the primary and the secondary rainbows? Why it is bright white below the primary? What conditions are required to see a rainbow? Let us learn more on rainbows here. The first person to scientifically explain rainbow was Sir Isaac Newton. In 1704, Newton was the first scientist to provide a convincing scientific explanation for rainbows. First, Newton demonstrated that white light, sunlight, consisted of a spectrum of colors. When he sent a narrow beam of sunlight towards one side of a glass prism, what came out, on the other side, was a spectrum of colors as in the picture. This chromatic dispersion is caused by a phenomenon called refraction of light. Second, Newton also understood that the refraction of sunlight could happen in other substances too, such as water. He also realized that water droplets, in the atmosphere on a rainy day, could act as tiny prisms that enabled the splitting of sunlight into its component colors. Before getting into the physics of rainbow, we need to understand some of the basics of refraction and reflection first. Reflection. Picture here shows a narrow beam of light called incident white light, traveling from left through air at an inclined angle, which encounters a flat glass surface. Part of the incident light is reflected by the surface, forming a beam directed upward inclined to the right. Please note that the angle between the normal and the reflected beam, called the angle of reflection, is equal to the angle between normal and the incident beam, called the angle of incident. This is the law of reflection. Both the angles have the same value, θ1. Refraction. What happens to the rest of the white light at the glass surface, which is the interface between air and glass, is more interesting. It gets bent at the surface, because glass reduces the speed of light as it enters the glass. As we can see in the picture, the amount of bending depends on the wavelength of the color of light. Bending is greatest for violet and is least for red. Other colors lie in between these two. The splitting of white light, due to refraction, is known as chromatic dispersion. The key point is that this chromatic dispersion can also occur when sunlight falls on a water droplet too. Now let us investigate what happens in a water droplet in rain clouds. Let us consider a ray of sunlight that falls on a raindrop, at point A. A part of it refracts as it enters and separates into its component colors, as in a glass prism. Red light bends the least, as we have seen in the refraction section earlier, while violet bends the most. Other colors bend in between these two. All these refracted rays travel to the other side B of the raindrop. At the point B, some of the rays reflect internally and travel to the point C, where it refracts again to exit the raindrop, almost reversing its original direction. As they exit at point C, calculations show that red light can come out of a raindrop between 0 degrees and 42 degrees, the max, while violet can reverse the course between 0 degrees and 40 degrees, the max. This is one of the key points to note in order to understand the science of a primary bow. Another key point is, even though the red color can emerge out of the raindrop anywhere between 0 degrees and 42 degrees, the intensity of red color is dominant at 42 degrees. Similarly, violet is dominant at 40 degrees, though it can come out anywhere between 0 degrees and 40 degrees. Other colors are dominant in between these two colors. Thereby, this droplet creates a band of colors violet at the 40 degrees end and red at the 42 degrees end, while other colors fall in between. Now, let us explore how the splitting of sunlight by millions of droplets in the atmosphere results in a spectacular primary bow. Let us first focus on how the primary bow forms. To see a rainbow, 3 conditions are to be met. First, the sun should be behind the viewer. Second, there must be plenty of water droplets in front of the viewer in the sky. Third, sunlight should be able to reach the water droplets. There should be no obstruction between the sun and the water droplets in the sky. If the above conditions are met, When you look at the sky at about 42 degrees from the reference line, as shown in the picture, you should be able to see a primary bow. The reference line is an imaginary line that connects your head and the tip of your shadow on the ground. You can see the red band at 42 degrees while the violet-blue band appears at 40 degrees, and in between lie the rest of the colors orange, yellow and green. Below 40 degrees, that is, below the primary bow, it is just white bright light because all the colors are equally present from 0 degrees to 40 degrees. When all the colors of equal intensity are combined, we see just white light. And above 42 degrees, that is, above the primary bow, and up to 50 degrees, there is no light coming out from the water droplets, and therefore it is a dark band between 42 degrees and 50 degrees. What happens above 50 degrees? You may see a faint secondary bow above 50 degrees because of the second internal reflection of light inside the droplet. Look at this amazing double rainbow. Have you ever seen such a double rainbow? When we see a rainbow, most likely, we only see the brighter bow, which is the primary bow. The fainter bow, which is outside of the dark band, is the secondary bow. It is easy to miss the secondary bow because it is barely visible in many cases. The dark band, between the primary bow and the secondary bow, is known as the Alexander dark band. Have you noticed anything interesting about the order of the color bands in these two bows? The color bands are precisely in the reverse order. The primary bow has a red band outside and a violet-blue band inside. But the secondary bow has the red band inside and the violet-blue band outside. Next time when you look at a rainbow, try to see all the parts and enjoy the beauty that nature presents. If you would like to read more on similar topics, please visit AmazingPhysicsForAll.com. Thanks for watching.